All right, good morning, good evening, good afternoon, depending on when you're watching this. I just created these videos just to give a little refresher on some topics discussed during our class meetings. Okay, so we're watching this in preparation for our exam come next week, or coming soon, I should say. So one thing I want to just kind of remind you about is how we found these empirical probabilities. So how we found empirical probabilities was either by data, and from the data we would estimate the probability, like when we're talking about political party and Syrian refugee opinion. And other times we use simulation, like how we did for kissing the right way example, or when we're flipping the coins. So I want to talk about that simulation again and emphasize again how we can do that in Statcrunch. So as far as simulation goes, I mean, they have these steps labeled out here. So one is identify the random action and the probability of a successful outcome. So before it was, 50, we flip a coin, and 50% chance couple tilt head to the right, 50% chance they tilt the head to the left, right? So the random action there is the direction of head tilt. And then in 2, we well, how do we simulate this random action? And so in class, I let everybody borrow some coins, and we were just flipping a coin and recording the outcome 20 times. And then of course, we also use Statcrunch, which helps simulate flipping a coin for larger sample sizes. And then we say, well, determine the event that you're interested. So in there, we were counting the number of head tilts to the right, or counting the number of heads, but we need to determine what are we counting here. And then of course it says we want to explain how you simulate one trial. So either we were flipping a coin, or we're relying on Statcrunch to simulate that flip coin. And then of course we carry out a trial, meaning we flip the coin or let Statcrunch run, and then we record whether or not the event of interest occurred. So really we recorded the number of times there was heads, or number of times head tilts to the right, out of the total number of couples observed, or total number of coin flips that were done. And then of course we repeat this many times, at least 100. And then we count the total number of times the event occurred. Okay, so here when we open up Statcrunch, we recorded the number of times we observed 18 of 20 couples tilt their heads to the right out of these total 100. Right, so we simulated the 20 coin flips 100 times, and for each 20 we counted the number of heads. Right, and so we put the number of heads of interest over the total number of simulations. And so it says the number of times, let's fix that. It says the number of times the event occurred divided by number of trials is your empirical probability. So really quickly here, it says something here about Lazar's numbers. I mean, we could rely on this way to estimate probability. But if we look in this example of rock, paper, scissors, you may have played the game before. You go rock, paper, scissors, shoot with one other person. And we know that you have 3 selections: rock, paper, and scissors. We know rock beats scissors, paper beats rock, and scissors beat paper. Okay? And so in this game, what they're saying here, Shushaling, which is probably one of the earliest names for rock, paper, scissors. But it says, have you ever played rock, paper, scissors, Rochambeau? It's considered a fair game in that 2 players are equally likely to win, kind of like a coin toss. But what they're saying is that, so in here they're saying, they're kind of explaining the game, and of course there's a website. So really what they're pointing out here in the study, they're saying, but is it really a fair game? Do some players exhibit patterns in their behavior that an opponent can exploit? So what they're saying here is that, players that are relatively new to the game tend to avoid scissors. Okay, meaning each outcome is not equally likely, that they're more likely to select paper or rock versus scissors. So what we're going to do, we're going to test this out. We're going to just, what if we were to play this game with a friend of ours who hasn't played the game before, and we play 40 times. Okay, so we're doing rock, paper, scissors, shoot, rock, paper, scissors, shoot, 40 times, and our friend picks scissors 8 times in those 4 plays. So what we want to do is we want to use empirical probability here. Okay, we want to use this empirical probability here of this. We want to find the probability. What's the chances that we observe 8 out of 40, given that there's no preference in rock, paper, or scissors? So meaning, how do I simulate this experiment where the probability of scissors is 1/3? So meaning that there's no preference here. So in this case, we can't flip a coin 40 times and count the number of heads, because probability of heads is 1/2 or 50%. So, but probability of scissors is 1/3. So I don't have a coin laying around where I know 1/3 chance heads, 2/3 chance scissors. So we really need Statcrunch in an example like this. And so, yeah, that's what I'm saying. We cannot flip a coin like we did for kissing the right way. So we're definitely going to have to use Statcrunch. So in Statcrunch, what we do, we just go to simulate Bernoulli again. And so my number of rows, 40, is the 40 games played. And my columns, 100, well, that's 100 trials. And my probability of success, or probability of scissors here, is going to be 30%. Okay, so this part here is what allows us to get away from flipping a coin. Okay, if you don't have a coin, no big deal. Even if you had one in this case, it wouldn't help us. So this, what it does for us is kind of create a coin where it's 30% heads. Okay, now of course, remember for each trial, I'm going to count the number of scissors selected out of the 40. Okay, so I'm going to play rock, paper, scissors 40 times. Probability that my friend selects scissors is 30%. After each game of 40, I'm going to count the total number of scissors out of 40 plays. Okay, and I'm going to repeat this game of 40 100 times. And then what I'll do is I'll get my outcome. I'll get my outcome of my distribution of expected outcomes like we did before. Okay, so if I were to do that for this particular example, so what all these dots represent are the number of times scissors occurred out of 40 plays, and we did this 100 times. So we see there's a couple of times where 20 out of 40 were selected. We see there's a lot where 10 out of 40 were selected. And what I have highlighted here in pink, this is the number of times that 8 scissors out of the 40 were selected, right? So these represent all the different outcomes of the number of times scissors was selected out of 40 plays, given that the chance of scissors was 1/3. So if we want to find the probability of observing 8 out of the 40 plays scissors, well, we just put the number of times we observed this, and in this case, since I highlight it, it gives me 6. So at 6 times I observed 8 scissors selected out of the 40 over the total number of simulations. So remember, I ran the simulation 100 times. So we roughly get a 6% chance of observing 8 scissors selected out of 40 plays. Okay, just to just show you. I just go in here to data, and then of course I go to simulate, and I go to Bernoulli. So this Bernoulli is kind of like flipping coins idea, and then I'm saying, well, we're gonna play rock, paper, scissors 40 times. I'm gonna simulate this game 100 times. Probability of scissors is 30%. And then in here, I want to count the number of times scissors was selected. So I'm going to do sum, and then my result here. And then I'm going to say okay. And then I can just run it as so. Okay, so I run it like this. I hit compute, and then I get all my outcomes here. So this is saying for game 1, my friend selected it 10 times. For game 2, he would have selected 11. For game 3, they would have selected 11. For game 4, they would have selected 18. Right? So we could graph this distribution. So there I'm using a dot plot. So I use a dot plot for this. And there we go. Okay, now due to simulation, you know, they're not always going to look the same. Okay, not always look the same. So if I find 8 here, which is right here, so this is sum of 8. So if I highlight there, in this case, I'll get I'll get 5. So in this case, I'll get 5 out of 100, which is 5%. Okay. All right, but this is just a quick reminder of how we can use Statcrunch here as a really powerful tool to calculate very complicated probabilities. Now, of course, one thing that I can do here to improve my simulation is I can increase this. So I could increase this to 10,000. Right. So the more simulations you have, the better. And if you compute this here, right, what it did automatically was simulate 1,000 games. Right, so this goes all the way down. If I scroll all the way down, I'm sorry, 10,000. It did 10,000 in the blink of an eye. Okay, and if I were to create the dot plot for that, okay, the dot plot for that, it would look like this. Whoa. And I mean, you know, we kind of got into the topic of binomial looking like a normal distribution. And we know that this looks like a binomial here. But if we look here, let's see 8 appeared here. So let me clear this really quickly. So 8 appeared right here. So in this case, now we get 560 times. 560 times did 8 appear out of 10,000. Okay, 10,000. Okay, but this probability would be more accurate given that we ran more simulations. Okay. All right, but I just want to give you that. These slides you can find, they're on Canvas, okay, involving probability here. And, you know, just to give an example. But just a reminder there as far as how we do the simulations, a very powerful tool here, okay.